Hi everyone, welcome to my new video. Today I want to take a look at doing some evil stuff. I want to take a look at writing some ransomware in Rust. My name is Michael Mullen, and let's get started. But before we get started, I want to put up a disclaimer. Um, this video and the code that I'm showing you is for educational purposes only. I take no responsibility for any of the harms done by you by using this code. The usage of someone else's computer without their permission is a crime. People have been given long federal prison sentences for doing ransomware-like things, so don't do bad stuff. Now, of course, why are we doing this? We're doing this for two reasons. The first reason that you need to think like an attacker to be able to defend against attackers. I think Sun Tzu said something like, "You need to know yourself and to know your enemies," something like that. Um, and the other reason is because one of the main kind of things I'm about to teach you are some cryptographic concepts, and sometimes it's fun to learn about things when you're pretending you're a bad guy. Like when you're doing evil, sometimes it's fun to do that. So I'm a little bit worried about putting this video up because this code is written in Rust. This ransomware is going to be very performant. It's going to be very small, and hopefully, because I'm teaching you some cryptographic concept, it's going to be very it's going to be fairly secure as far as the cryptography goes, which means that it's a really good launching place for someone to make a real ransomware application with. So I'm a little bit worried about putting that out into the world. So I don't think I'm going to be sharing this code on GitHub. Obviously, if you want this code, what I suggest that you do is email me saying who you are, that you watched the video, and that you want this code, and I'll try to figure out a way to get it to you. Maybe I'll tar gzip it or something like that. And I'm also going to put in this video 3 passphrases for you to put in this email for me to know that you aren't just some dude that wants ransomware code to kind of do bad things, but you're actually a viewer of mine and you watch the video and you're asking for the code to better understand these concepts. So yeah. Now, before I get started, a few months ago, one of my viewers named Morris sent me an Amazon gift card. And I used that Amazon gift card to buy myself a book. So I bought myself, from this Amazon gift card, this book called Dungeon World. And, sorry, let's get it more in focus here. Dungeon World is a tabletop role-playing game, something like Dungeons and Dragons, but it's a little bit easier to understand. The rules are a little bit simpler than Dungeons and Dragons. So hopefully, sometime in the future, I will be using this book to run an evil characters campaign to say thank you to Morris. So yeah, thank you, Morris. I really appreciate it. All right, so what are we going to learn by doing evil? What are we going to learn in this presentation? What you will learn is public key cryptography. We're going to learn about things like Diffie-Hellman and how to use Diffie-Hellman with Rust crypto in Rust. We're also going to be learning about some symmetric key cryptography that will do the actual encrypting of files. And that we're going to be doing symmetric key cryptography using the Cha-Cha 20 cipher stream cipher. You will also learn like a few other like Rust techniques, like using the walk-dir crate. You're going to learn about augmenting the standard IO file, the standard file from Rust. You'll also learn some more Rust stuff, some interesting Rust stuff that doesn't necessarily have to do with cryptography. Um, so yeah, what you will not learn, you won't learn about infiltration. So how infiltration or privilege escalation. So before you run a piece of ransomware, you need to have access, like a web shell onto your victim's machine in order to actually deliver this payload that I'm going to be demonstrating to you, and having the um, advanced permissions, advanced privileges in order to read and write from the files that you're going to be putting under ransomware. Um, I will also not teach anything about target file enumeration beyond how to use Walkter. Um, and what I mean by target file enumeration is like which files are valuable to the victims, because yeah, you like just encrypting a bunch of like useless stuff. No one's gonna pay you for that. Pretending like we're evil here. You have to like you have to find what files are actually valuable to the people you're targeting, and those are the ones that they'll pay for. I will also not teach you about any evasion techniques, about how to get away with extorting people on the internet, because even if I did know, I don't. Even if I did know, I wouldn't tell you how to do that. Actually, maybe I would, but I don't know. So yeah. So I've broken this up. I've broken this project up into 5.5 pieces, and they're kind of building one on top of the other. Um, the first piece is called basic, and in this binary, I'm going to show you how to generate an elliptic curve Diffie-Hellman key pair. I'm going to teach you how to use two key pairs to join together to make a shared secret, how to use an HKDF to take that shared secret into proper unified keying material, and how to use that keying material to encrypt files, to encrypt data. The next step is file enc demo, which basically does the same thing, but now we're gonna like access the file system, and the data will be on disk. So we're gonna be encrypting and decrypting files rather than just kind of strings that the user types in. The next step is kind of like the file encryption demo, but done in two separate stages, and it's sort of more to represent the stereotypical Alice and Bob want to send data to each other over network traffic or something like that, and how to use cryptography to share a secret message between two separate parties. The fourth step is a ransom, and the ability to a ransomware and the ability to provide a victim with the ability to decrypt a file that has been ransomed. But there is going to be a major problem in this that I'd like to show, and that will be the half step, the 0.5 step. And then the final step will be a real ransomware most valuable product, minimum viable product. Now, this isn't going to be like a full-fledged ransomware where, like I said, there's no kind of target file enumeration done on this. It's just going to encrypt everything in a directory. There's not going to be a fancy way to tell the user how to go about paying us. But yeah, it's going to be a minimum viable product that I am worried about going off into the wild. So yeah, let's jump into the code. Okay, so first of all, like I said, I'm worried about this code, so I have a special license to it. The code that I'm showing to you is like the opposite of open source. I am reserving all rights over this code. This code is for educational and research purposes only. You may not do the following with this code. You may not use this code for illegal purposes. You may not distribute this code. You may not copy this code into another project. And you may not use the binaries derived from this code on computers in which you do not own. Okay, so we got the disclaimer and the license out of the way. Let's look at the first binary, and it is called basic. And let me give basic a compile and run. So I have a special builder script here that in which I'll go into in the future, at the end of the video or something like that. But yeah, it's just a compiler, and it also copies the binaries into the same folder that I'm working on right now. So yeah, I've got the basic all ready to go, and I will give it a run, and I will pass in the H parameter to see what parameters I can use, and there is an input parameter. So I will input, hello, my name is Michael. And what happens here is that I am generating a elliptic curve key pair and dumping that to the terminal. I am then creating another key pair and dumping that second key pair to the terminal. I'm then using elliptic curve Diffie-Hellman to join those two keys. I'm then using an HKDF to make sure that I have unified randomness over a shared secret. And I am using that the HKDF output to give me a key in which I am encrypting that hello, my name is Michael data. And the keys are such, and the ciphertext turns into this. And then I am decrypting it. I am decrypting this data, and I get back my hello, my name is Michael. So let's look at that code. So here is that first step where I'm generating the key pair and dumping it to the monitor, dumping it to the screen. I am then doing that a second time, getting a second key pair and dumping that to the terminal as well. And I have named these priv1 pub1 and priv2 pub2. I am then using elliptic curve Diffie-Hellman with private key number 1 and public key number 2 to get a shared secret, and from that shared secret, HKDF into a key that we can use for encryption. And so let's, and I'm doing that again, getting another key using the private key for the second key pair and the public key for the first key pair. So yeah, if you're unfamiliar with Diffie-Hellman, the idea is that when you create a key pair, you create two keys. You create a public key in which you can share with anyone, and a private key in which you must not share that key with anyone. And another person will make a key pair as well. Now, so we've got four keys. We've got public private number 1 and public private number 2. When you take private number 1 and public number 2, you can do a Diffie-Hellman on those to get a shared secret. You can then take private key number 2 and Diffie-Hellman that with public key number 1. And when you Diffie-Hellman those two together, you will get a shared secret, and that shared secret is the same as the previous shared secret. So that's how you're able to kind of get keying material from Diffie-Hellman, and that's what this public key cryptography is all about, is sharing your public key with someone, them sharing their public key with you, you joining your private key to their public key, and them joining their private key to your public key. And when that happens, the shared secrets are the same. So that's where the magic is. That's how the internet works, basically. So yeah, let's see a little bit more deeper into the code. So we're going to look at the key pair generation function. And what we're doing here is we are getting the cha-cha random number generator. So the cha-cha random number generator is something called a cryptographically secure pseudo random number generator. And what that does is that when you give it a seed, it will give you cryptographically secure bits when you ask for them. So you can ask for, I want 32 random bits. and the random number generator will give you 32 random bits that are cryptographically secure. Now, this is a pseudo random number generator. So if I were to seed the pseudo random number generator with the same seed value multiple times, it would spit out the same bits in the same order. So we want to have like our seed come from something with a high amount of entropy. And the best way to do that on Linux, as far as I know, is from the system call get random. And that's what this from entropy call does. It calls get random to ask Linux for a random seed. Now I've made this code to be able to accept a seed given by the developer, but I've never enabled it. So that's for future work. So right now it's just getting random entropy from the kernel, and then it will put that into a cryptographically secure pseudo random number generator for later use. Now we immediately use that pseudo random number generator to create the private key. After we create a private key, we can then generate the public key associated to that private key. And then we dump those both out to as the return value of this function. And then to dump these keys, what I'm doing is that I am converting these keys into something called a PEM format. And the PEM format is this. It's kind of a way of dumping out those bits in such a way that you can read them on the console, basically, or copy them into an email, something like that. It's the same as what you see inside of if you've ever done an SSH keygen, and you've got that ID _ 25519 file. It's the same concept as that. That's a PEM file. So yeah, I'm generating the public private key pair, dumping it out to the command line. Now, of course, I still have them in memory. I then make a second key pair, and then we get towards the Diffie-Hellman work. So let's jump into the getting a symmetric key, and I will be using Diffie-Hellman. So the main part of this is to get a shared secret from the Diffie-Hellman joining the public and the private keys together. Don't worry too much about these methods here. They're just the way that you do it. It's just important that we're taking the public key and the private key, joining them together, getting the shared secret. Now, the shared secret might not be uniformly random. What does uniformly random means? What it means is that, say I have, I want a key of 16 bits. Uniformly random means that every bit of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 has a 50% chance of being either a 0 or a 1. So it is uniformly random. Every single one of those bits has the same chance at being a 0 or a 1. Now, I am not 100% certain that the result of a Diffie-Hellman is not uniformly random, but because I am not sure, I am going to pass the secret key through an HKDF. So an HKDF is an HMAC, a hashed message authenticated code function that will make sure that our keying material is uniformly random, and it will make sure that it is the size that I desire. Because I don't want a 16-bit key, I don't want a 128-bit key, I want a 256-bit key. So what happens here is that I'm going to use the shared secret, and I'm going to extract using the SHA-256 algorithm. So that's going to make sure that everything's uniformly random. That's what the SHA-256 is doing. I'm I'm going to pass in a salt. Now I don't need to do this, but it's kind of a, it'll add a little bit more entropy towards it. And it'll also make sure that if I update my versions of this piece of software, it will mean that version 2 will not be compatible with version 1, because my salt is where I'm putting in my versioning information. So we don't need to add the salt. It's not actually adding anything for us. It's just making things more, I don't know how to best describe it. It's not adding more entropy, because it's already uniformly random. Therefore you can't add more entropy to that. It is making sure that our versions do not align with each other, so you can't accidentally use a version 2 piece of software with a version 1 piece of software. But that's basically all it's doing. So yeah, I'm getting my HKDF algorithm, and then I'm using that HKDF algorithm to expand the keying material into 256 bits, and I am storing that in the value key with this expand. I am then making a cha-cha-20 key from this, and it's just like a nice wrapper around the key that I have, in which the Rust crypto library understands how to use this key wrapper. So it provides like traits and things like that, traits and methods for easier use in the Rust crypto library. Then I am zeroizing the key that I derived so that the keying material is only in the key. Now, this isn't really necessary for the project that we're doing today, because so what I'm doing here is making sure that the memory location on RAM, the RAM is it inside of the RAM on the computer, on the physical chips. That key is known. In highly secure environments, in say you're a Navy SEAL and you've got a special cell phone, and your cell phone could be captured by the enemy. You want to make sure that if they get your phone, they dip your phone in liquid nitrogen and pull off the RAM chips, that those RAM chips do not contain the keys to decrypt any top secret information that you have on your phone. That's really the only reason why you would want to zeroize stuff like that. It's just because of where the cybersecurity company that I used to work for did sometimes sell products to people who used our products for highly top secret things. So the key zeroization is just kind of in my mind. It's just kind of a good practice that I've gotten myself into. Anyways, yeah, you don't need to do it, but I'm doing it here because I've been trained. I've been trained to do it, right? Okay, so we've got ourselves a key that we can use for cha-cha-20 encryption. So then I get that key again, but this time using the opposite sides of the key pairs. So this encrypted key should be exactly the same as the decrypted key because of the properties of Diffie-Hellman. I'm then going to use the encrypted key to make a cha-cha-20 poly 1305 cipher, and then encrypt the data that I passed in to a piece of ciphertext. Now, cha-cha-20 poly 1305 is actually an AEAD cryptographic primitive. And what that means is that not only does it encrypt the data, but it ensures the authenticity of the encryption such that if someone were to manipulate the bits in the file after it has been encrypted. So someone has tampered with the data. The data will no longer decrypt properly because the kind of the concept of the AEAD is that it is better to fail than to go forward with tampered information. That's the idea of the AEAD part of the Cha-Cha 20 Poly 1305 cipher. So yeah, I create the ciphertext. I then use the ciphertext and the decryption key to decrypt, and I dump out the information onto the screen. So let me go through that one more time. Here is the first public-private key pair. Here is the second public-private key pair. Here are the keys, and of course they are exactly the same. Here is the ciphertext, and then here is the decrypted plaintext code. So the first passphrase for getting the source code is the word for, F-O-R. All right, so let's move to the second part. And now I'm not going to go over the keying material or anything like that. Now we've gone over that. Basic was kind of the most learning part. Now we're just kind of getting into more and more interesting things and kind of building ourselves up a little bit faster than we did on the basic function. All right. All right, so in this case, we're again going to be generating two key pairs. We're going to be using those key pairs to make keys. And then we are going to be encrypting files instead of just a string that we pass in on the command line. So in order to do that, I am going to give this encfile function 4 things. The first thing is the file containing the plaintext. The second thing is the file that will contain the encrypted data. The third is the key. And the fourth is something called a nonce. And a nonce is very, very, very important as far as stream ciphers go. But I want to get into that a little bit later. Just keep in mind that that nonces are very, very important. And as of right now in this piece of code, I am using it wrong. And the reason why I don't want to get into how I'm using it wrong is because I want to demonstrate how I use it wrong so that you can see, like, oh shit, you can, like, if you fuck up with the nonce, you really fuck up. So yeah, I am opening up the plain text file. I am making a buff reader so that we can read the information in a Rust idiomatic way. I am creating the file that will contain the encrypted data, and I will make a buff writer so that we can write to it in a Rust idiomatic way. I am then getting myself an array of buff size in length, and this will be what holds both the data that for this file, it will hold the data that we read from the plain text file, and it will be always of an exact size until we hit end of file. And for this time, the amount of data that we're going to be storing on the stack is 50,000 bytes. I create my cipher, and then I read from the file, read from the reader. So the reader is the plain text file, into this array, this stack-based array. I read it exactly 50,000 bytes, or we only stop when we hit the end of file. So this is another little bit of learning about Rust that you might find interesting. Rust provides you can either do a standard FS read, or you can do a standard FS read exact. Neither one of these are exactly what we want. So a read, if we do a read on into our mute data, our mute data is 50,000 size. And for encryption purposes, I want to ensure that I get exactly 50,000 bytes here. Because if I get less, if I get less bytes, so if I do a read and I ask for 50,000, but the kernel only gives me 40,000, I'm in trouble here because the nature of encryption means that I need to store how much data I actually encrypted, because I will only be encrypting for this time 40,000 bytes. So I need to like store in the file or something like that I have encrypted 40,000 bytes. This is a problem because I don't want to store that information. I don't want to store the sizes of how much I encrypt. I want to encrypt 50,000 bytes, then 50,000 bytes, then 50,000 bytes. And if I hit the end of file, I want to, before 50,000 bytes, then I want to encrypt everything I can. So yeah, that would lead us to the read exact function. Now the read exact function will give us 50,000 bytes every time, except it will throw an error if it reaches end of file. So let's say we have a 90,000 byte file. Read exact will give us 50,000 bytes, and then it will error. So that's no good. We want to like encrypt all of the data in the file. So that's why I wrote the function read exact or EOF. And this function is very, very similar to the read exact function that you can find inside of the standard library. In fact, let's see if we can just jump to it. Standard file read exact. See if I can jump to it. No. You can look it up for yourself. It's basically a copy and paste from read exact with a few small changes to keep track of the size in the case that we don't actually hit 50,000 bytes. Okay, so we've got the exact amount of data that we want to encrypt. And we do the similar to the basic the basic binary in that we just encrypt this data, and we encrypt it. We encrypt it and we get the ciphertext, and then we write the ciphertext to the writer, which is the encrypted file. Okay, and then we want to go about decrypting that stuff, and it's exactly the same but in reverse. So now the file that I'm building my buff reader from is the encrypted data, and the file that I am building the buff writer out of is the what will be the plain text, and it's the exact same sort of thing but in reverse, and we call decrypt instead of encrypt, and we do the write. Yeah. I want to get out of here and status. I want to get to restore source.file demo. Okay. So let's give file demo a run, and we can see it in action. Build file inc demo. All right, so the way in which we do this is we file enc demo, we give F, and I'm going to give it some data inside of a test data. And I have this 500 worst passwords file that I would like to encrypt. I will encrypt it to a file called enc, and then I will decrypt to a file called dec. And it's all done. And if I take a look at enc, we will see that it's all gobbledygook. And if I take a look at dec, we will see that it's a bunch of passwords. And in fact, it is, if I diff the dec to the test data 500, we will see that it is the same. So yeah, the basic file demo works as well. Let's do a clean and get rid of deck and enc here. All right. Now let's jump to the next demo. And the next demo requires kind of two binaries to run. It requires the binary called key pair, and it requires a binary called file. So let's look at key pair first. Key pair is very, very simple. It does it generates that public-private key pair, and then it dumps it out to a file called name. We've seen that before. So let me run that. And the other one was called file. So what this demo will do is similar to the file enc demo, except it will be like 2 stages of running. And it's sort of to demonstrate the Alice and Bob traditional description of how to do cryptography over the internet. This is not secure enough for internet communications. This is only for demonstration purposes. And the reason for that is because in my previous binaries, I was using the Cha-Cha 20 Poly 1305, which gives us authentication assured data, authenticated encryption assured data, AEAD. In this demonstration in file, I got lazy and didn't use Cha-Cha 20 Poly. I am just using Cha-Cha 20, which means that there's no authentication. So that's why it's not good for internet communications. Just to remind you, the authentication means that if I were to encrypt a file to send to a guy named Bob over on the internet, someone man-in-the-middles me and manipulates that data, tampers with it. Bob has no idea that that data has been tampered with unless I use an AEAD assurance mechanism for my data. That's why that's important. But yeah, I was lazy, so that's why you shouldn't use this. Okay, so we've got it all encrypted, or we've got it all compiled, and I want to first generate a key pair. And I'm going to generate a key pair for a lady named Alice. And then I will generate a key pair for a guy named Bob. And we're going to pretend that Bob and Alice are not on the same computer right in front of me. We're going to pretend that Bob is somewhere on the other side of the world and that Alice is sitting right beside me. So I now have Alice's key pair, and I'm going to pretend that Bob over on the other side of the world has his key pair. Now I'm going to get Alice to send her public key across the world to Bob. And I'm going to get Bob to send his public key back across the oceans to Alice. Okay? So when I am Alice, I have access to Alice Priv and Bob Pub, and also Alice Pub, but I don't use Alice Pub. I only give that to other people. Bob has access to Bob Priv and Alice Pub. Okay? So now I am going to run this file application. And what I will do here is I will encrypt that test data 500 again. And I'm going to put it to enc. And I'm not going to be decrypting it because I don't want to decrypt it right now. And then I'm going to use the private key of alice.priv and the public key of bob.pub. Okay. So now we have enc, and enc is a bunch of garbledygook. And Alice is now going to email that file over to Bob, and Bob will now decrypt it. And to decrypt it, we will do file dash F of enc, and we will decrypt it to dec, and we will use the private key of bob.priv and the public key of alice.pub. And now if we take a look at deck, we now have the 500 worst passwords in the world. So yeah, we've got that done. So let's clean ourselves up and move on. RM Alice's public private, RM Bob's public private, RM deck and ink, and let's do a build clean. Right. Oh, right. We want to take a look at how that was done. So it's very similar to the file enc demo before, but this time I've kind of abstracted things into a different module called encryption. And in here, we're basically doing the same thing, the same sort of stuff. Additions are that I'm taking notice of the permissions. This isn't really relevant yet. And I'm writing the permissions to either the encrypted or the decrypted file from the input file. And instead of using the poly cipher stream, I am just applying a key stream, and which I will get into in a moment because it's important for understanding why a nonce is important. So yeah. Now again, another thing that I'm doing here is that I am increasing my nonce. Again, I will get into why that is important in a second. So yeah, it's basically the same thing, except this is in 2 steps instead of 1 step. And it's using public-private kind of shared, like you would see on the internet. Again, don't use it. It doesn't use the poly. Okay. Okay, so now we're going to go to step 5 and step 5.5. And this is where I will be doing a naive ransomware. So this naive ransomware is called ransom. So I will build ransom and victim key. The second key phrase is educational. Okay, so we're all compiled up. We've got our ransom and we've got our victim key. Now I'm actually going to delete ransom here because I did this a little badly. I'm going to make sure that inside of the keys directory, I don't have any data. Now, if I try to build ransom, I will fail because there is something special that I'm doing for my ransomware. So what I need to do is get that key pair binary again. And using that key pair binary, I am going to make a public-private key pair called ransom. And what I'm going to be using this public-private key pair to do is embed the public key of the ransomware into the payload that I'm going to run on my victim's machine. And then in an application called victim key, I am going to embed the private key. So victim key will be used to generate a decryption key that the victim can use to decrypt their files when they send us some teddy bears or Beanie Babies or something like that. Yeah, let me demonstrate how this works. So I now have my ransom and my victim key binaries. Victim key, because it has the ransomware private key, should never go out anywhere. It's for my use only. My use as the bad guy only. And that's how we're making sure that that the good people that I am victimizing pay me. But anyways, yeah, let's run this ransom application. So I am going to run ransom on test data, and I'm going to do it on 100K most used passwords, and on that test data 500 worst passwords. And that's all I need to do. Wait, why? Oh, yeah, I need to give an F to both of them. Okay. So I have a little printout saying that this guy was encrypted and this guy was encrypted. And if you wish decryption, send the file for decrypt.pub to my super secret email address of elonmusk@twitter.com and send me 25 teddy bears. And if you do this, I will give you a decryption key that you can use. So the victim sees that their files inside of test data. So we've got this guy and this guy are encrypted. So let's just take a quick look, because we're gonna, no, you didn't ransomware me. No way did you ransomware me. And then oh no, you did. Shoot. Okay, I need to go buy 25 teddy bears and send them to elonmusk@twitter.com. Okay, so I do that and I send this for decrypt.pub. Now you'll notice that I'm also dumping the private key. I should not do that, right? Because I can join this private key with the public key found in the binary. And I will show you that strings ransom, and I'm going to pipe that to a file called S, and then we'll look at S. There is a public key right there, right? There is my public key. So I can take this data and join it with this data to regenerate the key. So if I were less lazy, I would of course delete the for decrypt.proof. So I'm just going to do that right now because let's do it. Okay, so now I cannot, I as the victim cannot decrypt this data, or can I? So I'm going to be naive, and I'm gonna pay Elon his 25 teddy bears and send for decrypt.pub. So back to being me as the evil ransomware, I am going to run my victim key program, and I'm generating a key. And I'm going to send this key over to the victim, and he will use this to decrypt his files. So let's do that. So the files are, again, these guys, but I'm going to pass it the decryption key. I hope this works. I don't think I actually tested this. Let's take a look at test data 500, see if it's now decrypted. Shoot. What about test data 100K? All right, what did I do wrong here? Provided the deck file with the deck key. Maybe I need to do them one at a time. At this point, I can no longer be sure of my data. So I'm going to go into test data, delete 100K most used, and delete 500 worst, and then find in my user I will find these again from my word lists. And probably all right, let's try this again. Okay, I'm going to ransom with test data of this guy, test data of that guy. Not going to provide a data encryption key. Then I am going to victim key for decrypt, get the key that the good guy will use. Right, and then ransom one more time. But provide the decryption key. Take a look at the test data. Okay, that's what it's supposed to be. And this guy again. Do it one more time and make sure it actually encrypts. Encrypted. Generate the key. We've got it. Okay. Now, this has a flaw. This ransomware has a really bad flaw in it. The really bad flaw is that, and this is where I'm getting into why the nonce is so important. So in my encryption, don't know why I opened it up like that. In my encryption, what I'm doing here, during my encrypt data, I am reading the data from the plain text file. I have the key, and I'm using that key and a nonce to generate the cipher. And a nonce is a number used only once. And what's important here is that for stream ciphers, you can never use the stream key and the nonce combination more than once. So you can use the key with any nonces so long as you never reuse the nonce with that key, and you can reuse nonces so long as you never use them with the same key before, but you can never use the same key nonce pair twice. So what's the problem here? The problem is, even though I am increasing my nonces, so it is fine to use a nonce as a counter. So my nonce here starts at 0, and then every time I do an encryption payload and I apply the key stream onto the data, I will increase my nonce by 1, and that's fine. There's nothing wrong with doing that in cryptography. The problem is, and the reason why I'm doing this is because I don't want to store the nonce in the file. So I will always start at 0, and I will increase up to whatever the largest integer value that 64 bits can hold. So I'm fine. I'm never going to run out of nonce identifiers here. So yeah, there's nothing wrong with using a nonce as a counter, but there is a problem with using the same nonce with the same key. So the problem here is that I am encrypting that first file. I am encrypting 100,000 most used passwords with the key, and the nonces 0 through whatever we end up at. And I am encrypting 500 worst passwords with the key and the nonce 0, the nonce 1, the nonce 2. So that's really, really, really bad. Unless you're the victim, in which case it's really, really good for the victim, because we as the ransomware people fucked up. And now the victim doesn't need to pay us because they have a way of getting their data back, even though it has been encrypted. This is called a plain text attack. So let's say that, as I showed you, when I screwed up with these files, you saw that they actually came from another place on my hard drive. And so these files aren't unique on my hard drive. They're just like, I just copied them here because it's easier to work with them in this area. But they are on my hard drive still. I've still got them somewhere else. I've got their plain text somewhere else. So let's pretend that I've got another file Let's pretend that I only have the 100K file somewhere else, but I do not have the 500 worst passwords file somewhere else. Let's pretend that. I can still get the plain text of the 500 worst passwords by using a plain text attack. The way that a plain text attack works is that what a stream cipher does is it takes your key, and I should show myself here because I'm going to use my hands. It takes your key, it takes your nonce, and it takes some other data. Like there's an initialization vector that is always like, it's like for 32-bit encryption purposes or something like that. It's like a phrase, and it's not like a special phrase. It's just like, it's an English phrase. And there is already another counter for the cipher. So it takes your key, it takes your nonce, it takes this initialization word salad thing, and there's a counter. So what it does is it takes those four things and it jumbles them up into a one-way function to come up with a key stream. Now the key stream is 512 bits in length, but will regenerate when the cipher needs more, keying material. So it takes this key stream and it XORs it with the plain text, coming up with ciphertext because it's using XOR encryption. The thing is, one of the properties with XOR encryption is that, first of all, let's pretend that I don't have these two files. I don't have test data. I don't have these two files anywhere else on my machine. It's still bad. There is still information that I can get out of these files. So the way that XOR encryption works is that it will take the key stream, which is uniformly random, and it will take the plain text and it will XOR them together to get the ciphertext. So it does that with the first file and the second file. Now, the key stream is going to be exactly the same between these two files. So that means that if I XORed these two files, these two ciphertext files together, what I would get out of it is the XOR of the two plain text. So it's still a XOR of the two plain text, which means that it's a little bit garbled, but because we're using the English language, we might be able to guess about, we might be able to extract the plain text for both of these files, because it is the plain text that is now XORed together. And that is certainly not uniformly random, right? It might not be readable like if I open it up in Vim, but I might be able to make it readable because it's two plain text files XORed together. Now, the other property of how XOR encryption works is that if I have my ciphertext and I have a plain text copy, if I XOR those two together, I will get the key stream out of it. So if I have the key stream, now I can decrypt. I can decrypt any file which used that same key stream that I've used. Now again, the key stream used for this guy to encrypt him is the exact same as the key stream used to encrypt this guy. Meaning that if I can get the key stream for this guy, I can use that key stream to decrypt this file without ever knowing what the actual key was. I hope that makes sense. If it doesn't, I'm about to demonstrate it, okay? Okay, so let's demonstrate how to get the key stream from a plain text and an encrypted file and use that key stream to decrypt another file. So we've got inside of the test data directory, we've got the 100K, we've got a copy of it, and we've got the 500 worst passwords. So I'm going to re-encrypt this 100K and this 500 worst using the ransom payload. Okay, so now they are encrypted, and take a look at them again. That guy's encrypted, this guy's encrypted, right? But I still have the copy of this somewhere else on my hard drive. Now I can use a plain text attack to get the key stream for the 100K and apply that key stream on the 500 to decrypt the 500, because inside of test data, I don't have a copy of the 500. So how do I decrypt it? I can use the plain text attack to do that. Now I have a little piece of code to do that, and that is called key stream. And in this key stream, what I'm doing here is I'm opening up the encrypted 100K file, the plain text 100K file, the encrypted 500 file, and I am making a new file for the 500 after decryption. And then what I'm going to do is I'm going to delete the encrypted file and rename the decrypted file to the 500 name. And what's going to happen here is inside of this function called XOR decrypt, I'm going to read the data, and then I am going to XOR the plain text and the encrypted versions of that 100K files together to get the key stream. And then I will XOR that key stream onto the 500K encrypted data, which will give me, the end result is it will give me the plain text of the 500K file. So that's really as simple as it is, and then I write it out to the file. That's all there is to it. So again, 500 is encrypted, so I will then build key stream, and I will key stream of the E is the encrypted version of the 100K file. The plain text is the plain text of the 100K file. And the target is the 500. Okay? And I'm not entering any keys or anything like that. This is simply making a plain text attack upon a stream cipher that reused a key. And therefore, because the key nonce pair was reused, these two encrypted files have exactly the same key stream applied to them. Therefore, if we get the key stream, we can decrypt the file that we do not have the plain text version of. Bam, got it back. Plain text attack successful. So, interesting, right? Now, there is a caveat to this. The caveat to this is that I used a larger file to get a key stream that can be applied to a smaller file. If this 100K most used passwords was smaller than 500 worst passwords, I would not be able to decrypt the entire file. So let's say I was able to do this in reverse, or let's say I had plain text and encrypted for 500, but I only had encrypted for 100K. Because 500 worst passwords file is only 3.5K in size, I would only be able to decrypt 3.5K of this file. So this is a problem that ransomwares in the field have made. Cybersecurity companies have been able to rescue victims because ransomware has just kind of gone willy-nilly over a file system and has encrypted a very large file, but somewhere else there was a copy of that very large file. So the cybersecurity firms were able to go, oh, here's the plain text, here's the encrypted version. It looks like the attackers are using the same key nonce pair multiple times, and because of that, the key stream is going to be the same, and we can apply that key stream to other files to decrypt them. And this happens if there is a very large file on the machine that was encrypted, but also has the very large file copied plain text somewhere else. So how do we get around this? We're going to be the attacker. How do we defend against this? And this is the last part of the presentation. This is where the real minimum viable product for a good ransomware begins in. And again, I'm a little bit worried about sharing this code. So again, the passphrase is for education only. Okay, so let's take a look at the real ransomware. So I'm going to clean things up now. Let's go back to test data and make sure that this is encrypted still. So I'm just going to copy my plain text back. Now, let's do a cleanup. And let's get rid of the for decrypt stuff. Okay, we're at a good start here. Okay. Now, I am going to build a application called payload and victim key again. So what payload is going to do is it's going to encrypt everything in a given directory with a unique key. Therefore, because it's always a unique key, there is always a unique key nonce combination. But the way that I've been making the keys is always has so far been using Diffie-Hellman to join a public-private key pair. What I'm going to do now is I'm just going to generate random keys, and I'm going to store those random keys into a file, and then I am going to encrypt that file with a key that comes from a public-private key pair. Okay, so let me give a demonstration about how this works. So I have down here in my code directory, I have this test ransom dir, and test ransom is the Linux kernel, and it has gone through the full make compile to compile up the BZ images and modules. So it is very large in size. It is 7.6 gigabytes in size. And if I open one of the files up, make file, oh, no, okay, I gotta delete this. Going from first principles. I'm not going to recompile the kernel this time. Test ransom, we can see that it is 6.8 gigabytes in size. Is that right? Okay, 6.8 gigs in size. Inside of learn, and also what I'm going to do is I'm going to find all of the files and make an MD5 sum of all those files and put them into this sums.pre file. And this is for checking to make sure that the encryption worked and that the decryption worked. So if we take a look at sums, we will see the MD5 hash of each and every file inside of the Linux kernel directory that is called code/test ransom. So yeah, there's lots of files in here, obviously. So now I'm going to deliver the payload, and I'm going to time this to see how fast it is. and it looked like it was about 3.5 seconds in length. We got a little message here saying what the victim needs to do. So what the victim needs to do is give me some Bitcoin and send an email containing a file called 4decrypt.pub to Elon Musk at twitter.com. So that 4decrypt.pub is just the public key that was used to encrypt this file. This file contains random keys and the files used for those random keys. So the file was encrypted with the random key. So it's a matchup between the random key and the file, so that we know what key to use to decrypt the file. But this file itself is encrypted using a public-private key pair, and the public key comes from me, the ransomwarer, the bad guy, and I have embedded that into the payload. So if we strings on the payload, and look for public key, we should find the start of it. Oh, why am I s-tracing it? That was string. String payload. Rep for public key. So we've got the public key here, and if I really want to, I'm going to dump that public key into a file called S, and we can vim that S and look for public key. And here is the public key. So this is my ransomware public key. Okay, so I'm embedding that in the encrypted in the payload binary, and it is going to be joined with a private key that is made during the processing of the application just once, and it is going to do all that asymmetric stuff that we talked about earlier in the video to encrypt this file that contains the files and the keys used to encrypt those files. So let's just make sure that those files are actually encrypted, right? Yeah, they're encrypted. But here's an interesting technique that I did. So I encrypted 1/3 of the file. So you'll see that there's plain text here, and then we go back to encrypted data. And then 2/3 of the file is decrypted still, is still plain text. And then 1/3 is encrypted. And this is to cut down on how much encryption that we need to do to just make the process faster. But encrypting 1/3 of the file is good enough to make the file not useful to the victims. They will still need to decrypt that data. Yeah, so the victim has this 4decrypt pub. They email it to Elon Musk at twitter.com, and then we run the victim key to generate a decryption key for this file here. And then we email this back to the victim, and they apply it along with the process about how to decrypt their files. And the way that they decrypt their files is they run the payload, they target that ransomware deck list, do not delete, and then they apply this key, and that is not the right key. And then they apply this key to decrypt their files. And let's time this as well. So the decryption was also pretty fast, about 3 seconds. And now the data is 100% decrypted. Okay, so how did I do this? So again, I am using for each this should have practiced this part a little bit more. So let's open up the source code. That'll help describe this. So there's two phases. There's the encryption phase and the decryption phase. In the encryption phase, what I'm doing here is that I am walking over the directory that that payload was given to encrypt. And I'm using a crate called walkdir. And then walkdir will walk over recursively the directories internal to the directory that we gave. And I'm going to look for every file, everything that is a file that isn't like a symlink or something like that, everything that is a file, and everything that does not have the extension ENC. And that's because ENC is the extension that I'm using to encrypt the file before I delete the original file and rename whatever file.enc to the original file name. So I don't want to like encrypt files that I'm already encrypting. Yeah, I get the full path of that file, and then I make a random key. So how do I make a random key? If you remember back at the start of this video, I used the cha-cha random number generator. And I'm going to use the cha-cha random number generator again. But this time, I'm just getting bits from the random number generator. I get 4 sets of 64 bits to give me a 256-bit key. Now, I believe that this is uniquely random, but I am not 100% sure. So I'm going to pass that through a KDF, and I have already described what the KDF does. And then I'm going to use the information out of the KDF expand function. So now I have 256 bits of unique randomness to make a real cha-cha 20 key. So now I have a real cha-cha 20 key that was generated with just random data. There was no Diffie-Hellman going on here. It's just purely random, and I have that key. So I use that key. First of all, I get a 64-bit version of that key, and I store that inside of a vector. So I've got a vector in which I'm storing the file names and the keys associated with the file names, and then I encrypt the file using that key, and I do the same sort of encryption that I've gone through previously in the video. So the only kind of unique thing here is that I am using a randomly generated key. So that key is just kind of coming out of the machine it's just random, right? There is absolutely no public-private key pair stuff going on. Completely random. I'm then getting a list of what that key has used to encrypt what file, and I'm just storing that in a vector. And I am using Rayon to make things go really, really fast. So because I have a 16-core 32-thread machine, I am able to do 32 encryption file. I'm able to encrypt 32 files at any one point in time. So that's why I'm able to get this so fast. That's why I'm able to get 6.8 gigabytes of data all encrypted in less than 5 seconds. So after I've gone through and I've encrypted all of the files, I'm going to take that key and name, and then I'm going to kind of join it up into a file format that is easy to understand. And what that file format looks like is it will have the name of the file, a colon, and then the key in the base 64 version. And then a new line, and then the next file key, the next file key. File, colon, key, new line. File, colon, key, new line. I then compress that data all up because there's quite a lot of files here, and I would get up in like 10, 15 megabytes of data here. So I'm going to compress that down to like 3 megabytes from 8. I'm going to compress that down, and then I am going to make a user's a user's public-private key pair. I'm going to use my attacker public key pair joining with the user's private key pair to come up with the shared secret, HKDF to unified random key, and then use that key to encrypt that data that is in the file colon key new line, file colon key new line. So I've got that data and I'm going to compress it and then encrypt it. And then I'm going to dump the user's public key to a file. And that file is what the user, the victim, will send to Elon Musk at twitter.com, along with paying him 0.1 Bitcoin. And when they do that, we as the bad guys will send back the key encryption key. That key encryption key will decrypt the ransomware deck list. It will decrypt it and then decompress it. And then we will one by one, again using Rayon, one by one go through it and decrypt all the data from the randomly generated keys that were stored in the file that was then compressed and encrypted. So let's go through the decryption path down here. So we open up that encrypted file, and then we decrypt it using the key that we emailed to our victim. And we were able to generate that key because we used our private key and the public key from the victim, and that came up with the shared secret, and then we hashed it to get the uniformly random key that we used to decrypt that file. And in that file, we have file names to decryption keys. And then we go through one by one and we just decrypt those files. And ta-da, we've got our ransomware going on. So the reason why this is a good start, a good minimum viable product for ransomware is very fast because it's Rust and it's using multi-threading. So as you saw, it went through 6.8 gigabytes of data in less than 5 seconds. Now, saying that, it's on a powerful machine, so, but still, that's really, really fast. That's, even on a 4-core 8-thread machine, it's still going to be pretty darn quick to go through 6.8 gigabytes of data. Also, there is a technique that I can use to... Now, did I actually decrypt my data yet? Did I actually show the full path here? Yes, I did. Okay. So let's do a clean, and there is a technique that I can use to get a very, very small payload. And this comes down to this build file that I'm using to build rather than doing cargo build. Let me show you how this build script works. All right. So as you can see, this payload is only 279 kilobytes in size. So that's pretty small for this kind of this ransomware, doing public-private keys, and I'm embedding a key right in it and stuff like that. It is also built using Musil, so it doesn't use any shared libraries, so everything that it needs is built right into that binary. So that means that it is deployable to different Linuxes. We can use this on any Linux that we want, so long as that Linux is x86. Yeah. So how do I do this? How do I get this payload? I'm using a shell script called build, and what build does is this is the main stuff here. So I am building normally Musil, but I can build GNU if I so wanted to. I'm normally building towards the target x86 unknown Linux Musil. And I am doing this with a nightly build, and that allows me to pass this build STD to give me a few more features. So this is to make it small. This is also to make it small, but the more important part about this is that in a normal Rust build, um, there is information about the paths in which you are compiling. Let me demonstrate that. Let me just do a normal cargo build dash. So in this normal build, we've got our target release payload, right? And it's got these. It's not statically linked, so it's dynamically linked here. But also, if I do a strings on target release payload, and I pipe it into a file called S, we look at S, I will see that there is somewhat personally identifiable information. So it's got the name of my home directory. So I'm a bad guy and I just put my username on my victim's machine. I might be going to jail if people see that, right? So what what this does, what this panic immediate abort does, is it gets rid of those. It gets rid of panic messages, and in some panic messages, personally identifiable information, specifically the path I used that holds my cargo directory, that holds my Rust compiler and stuff like that. That is embedded into my binary. So I'm getting rid of that from my binary. That's no longer in my binary. That's the most important part of this panic immediate abort. But also it makes my binary smaller. The next thing that I'm also doing is I'm using a tool called UPX. And what UPX does is it compresses the various sections of our ELF file, and it has a little decompressor built into the binary that when we run, we decompress all the different sections of our binary and run that, and therefore it's basically compressing our binary. It's compressing the various sections of our binary, and that means that we can get our binary very, very, very small. And it does not hurt performance. It does, but it's really, really, really minor. So let me clean this up, and let me get my payload and victim key with all of these tools compressing again. And let's see how long this takes to encrypt that Linux source code tree again. Okay, so let's first make sure that, yeah, okay, so I'm gonna run my payload over it and I'm gonna time it because I've got this specially compressed stuff. So how long does it take the compressed version of our, okay, it's really, really fast. Basically, it's a little bit slower, but it's basically still the same speed. So yeah, we've managed to really, really make our binary a whole lot smaller. And we're still very, very performant. All right, so last parting thoughts. The last parting thought is there is still a flaw in this ransomware code. And this flaw, I don't know how to get around, and I'm not sure it can be gotten around at all. I think all ransomware might be vulnerable to this flaw. And that flaw is that the randomness, the seed for the randomness has to come from somewhere. So in this case, when we look at the system call for the get random system call, I've done videos about BPF before. BPF can hook that system call, and it can see all the randomness that comes from that, meaning that we can see the seeds used to create the public-private key pair, meaning that in the case of payload, we can watch for get random using BPF. We can watch for get random, and that can be used to give us a seed used to create the private part of the victim's key pair. We can then join that private part of the victim's key pair. We can generate the private key from the seed, and we will get the exact same key because we captured the seed, right? And this is a pseudo random number generator. So that means that it is deterministic. It's cryptographically secure, but it is deterministic from the original seed. So that original seed needs to kind of be a nonce, right? It needs to be only used once. So if we can capture that seed, we can regenerate the victim's private key. If we can regenerate the victim's private key, we can Diffie-Hellman against the public key that is embedded in the payload, coming up with the shared secret. We push the shared secret through the HKDF, and now we have the key to decrypt this file. Once we decrypt that file, now we have all of the random keys used to decrypt all of the other files, and we can get all of our data back. So yeah, I don't know a way to get around that part of the flaw in this ransomware. If our victim is monitoring get random, they can see the seeds for the private key that we are using. They can also see the seeds for all of the random keys as well. So maybe they don't even need that, right? That if you're making randomness, you're coming up with that from a seed, and the cha-cha 20 cipher is deterministic, so we can regenerate so long as we get that seed. So yeah, someone watching get random is a flaw in our technique. Now you could say, okay, well, why don't you just embed a seed into your payload? Or here's a way to do things. You could run your payload and it could make a network connection to a different computer, and that different computer could send you the seed. But now you have the problem of your victims could be somehow monitoring network traffic. Now you could use proper end-to-end encryption. That might be a way to do things properly. Get your seed from a different computer, and therefore the victim cannot monitor for that seed. There's a technique that might be there, but that's a little bit more work than I wanted to do for this video. The video's already gone on for way too long. But there's a lot of information here, so I can't really make it any shorter. So yeah, right now what we have is a problem in how we generate the keys. If someone's listening to seeding, they can get around us. If they aren't, they're kind of fucked, right? They have to pay us. Fuck you, pay me. That's why I'm a little bit worried about this, because not too many people are monitoring their get random system call. So yeah, I've talked for way too long. I've probably given you way too much information, and your heads are exploding. My head's exploding. Look at all my sweaty hair here. Um, so yeah, I thanks for paying attention this long. Again, if you want to get the source code, you've heard the passphrase during the video. Email me at mazmullen@gmail.com. Um, and give me that passphrase that I've uttered over the video to and tell me who you are, just so that I know that you're not a bad guy. Tell me you're not a bad guy, please. I can't really verify that, but yeah, then I'll like tar zip the code and send it out to you. Um, yeah, I hope you've learned something. I hope you've learned something about cryptography, about ransomware, about public-private key pairs, about SHA-20, about how important it is to have a unique key to nonce pairing, about how to use Rayon, about how to use WalkDir, about how to make a additional functionality on standard file for Rust. Yeah, there's a whole lot of data here. I hope you've learned at least something. So yeah, have a good evening, everyone. See you guys later.